Deep under a mountain in Sichuan, China, sits one of the quietest places on Earth.
The deep underground and ultra-low radiation background facility for frontier physics experiments is 2,400 meters down underneath the Jinping Mountain.
It's the China Jinping Underground Laboratory, carved into rock more than 2 kilometers below the surface.
According to scientists, the extreme depth of the facility make it suitable for the study of dark matter.
There, experiments like CDEX are hunting for dark matter, the invisible stuff that seems to outweigh normal matter in the universe. Let's take a quick tour underground. Why hide a lab under a mountain? Tucking the China Jinping Underground Laboratory under a massive mountain sounds like something a secret agent would stumble into during a tense chase. But the real reason for this location is surprisingly down to earth. The universe is simply too loud. If you stand on the surface of our planet, you are constantly being hit by a rain of energetic particles from space called cosmic rays. Most of these are protons and bits of atoms launched into space by violent events like exploding stars and hyperactive galaxies. When they smash into our atmosphere, they create showers of new particles, including fast-moving muons that spread through the air, the soil, and even through us without us noticing. It is harmless for daily life, but if you are building a dark matter experiment that needs absolute silence, it becomes a serious problem. Scientists are trying to catch an interaction so rare that it might happen only a few times a year. Trying to do that while cosmic rays crash through the detector is like trying to hear someone whisper in the middle of a thunderstorm. At the Earth's surface, cosmic rays create countless false alarms. Every muon that zips through the detector and every neutron knocked loose by cosmic ray impacts becomes noise that looks suspiciously similar to the interactions scientists hope to see. This is why Jinping had to hide under a mountain. The lab needed a place where the sky would stop bothering it. Rock is one of nature's best shields. The deeper you go, the more protection you get as the layers of stone soak up or block most incoming cosmic rays. Physicists talk about depth in meters water equivalent because different types of rock block radiation differently. Instead of asking how many meters of rock lie above the lab, they ask how much water would create the same effect. Once you put enough overburden above the experiment, the number of cosmic rays drops dramatically. A few hundred meters make a huge difference. A few thousand meters make the world almost quiet. Jinping's tunnels hide beneath about 2,400 meters of mountain rock, which translates to around 6,700 meters water equivalent. That depth reduces the cosmic ray flow to a tiny trickle. Measurements show the lab gets only about 0.2 muons per square meter per day. That level of quiet makes Jinping one of the most shielded labs on the planet. But China is not the first country to look underground for answers. Labs in Italy's Gran Sasso region, Canada's Seno lab, and the former gold mines in South Dakota all use mountains or deep shafts to shield their sensitive detectors. Rock and earth act like a natural filter, blocking billions of unwanted particles while letting through the tiny hints of rare physics. What makes Jinping unique is how far this idea has been pushed. It is deeper than the others, and the mountain above it forms a shield thicker than any man-made structure could ever reasonably match. Depth alone is not enough, though. Even underground, the world is never completely quiet. Rocks contain small amounts of radioactive elements that give off particles as they decay. Building materials, dust, and even the scientists themselves add more background noise. When China searched for a place to build the lab, they did not just want a deep mountain. They wanted rock with very low radioactivity and stable conditions. The marble around the Jinping hydropower tunnels turned out to be ideal. It provides both depth and natural cleanliness, which gives experiments a much clearer environment to work in. There is also a subtle question researchers consider, which is the possibility that the Earth itself might block or slow dark matter if it interacts more strongly than expected. Teams at Jinping have explored how this might influence the signals their detectors can pick up. For the type of dark matter most experiments target, the benefits of shielding far outweigh any loss of signal. The silence created by escaping cosmic rays is worth far more than the small chance of missing a few interactions. Jinping Mountain is not hiding a secret. It is simply doing a job that no artificial shielding could do as well. By absorbing the constant rain of cosmic noise, it gives scientists the quietest room they can hope for while they listen for something incredibly rare. That quiet foundation sets the stage for understanding how the entire underground lab operates. The China Jinping Underground Laboratory. The China Jinping Underground Laboratory is not a single cave with a few machines humming in the dark. It is a full campus woven into the tunnels of the Jinping Mountains in Sichuan. The whole place began as part of the giant Jinping hydropower project along the Yalong River, and because the engineers needed long transport tunnels to reach the dam sites, physicists were handed an unusual gift. Instead of going down a mine shaft, they could simply drive straight into the mountain on smooth concrete roads that look like any modern highway. Only this time the road carries you more than 2 kilometers below the surface. That easy horizontal access is one of the lab's biggest advantages because it lets trucks haul in massive detectors and heavy equipment without the slow and expensive hoisting that traditional underground labs deal with. What makes this story interesting is that CJPL did not begin as a physics dream. It began as a civil engineering project on a huge scale. When researchers at Tsinghua University learned around 2008 that the tunnels under Jinping would be some of the deepest transport tunnels ever built, they saw potential. The midpoint of one tunnel sat under an enormous amount of rock, which meant excellent shielding for sensitive experiments. Before construction wrapped up, they worked out an agreement with the hydropower company to carve out special halls along one of the traffic tunnels. That move saved money and created a layout unlike any other physics lab, with quiet scientific rooms branching off the same roads used by trucks and workers heading to the dam. The first stage, called CJPLI, came together quickly. By 2010, the main hall and access drift were completed, and the lab was officially opened later that year. The early space was modest, roughly 4,000 cubic meters, but it was already remarkable because it sat beneath about 2,400 meters of mountain rock. That depth translates to around 6,700 meters water equivalent, which placed it among the best shielded laboratories on Earth. It did not take long before CJPLY ran out of space. The main hall filled with early experiments and screening stations, leaving little room for the next wave of larger detectors. The strong interest from the scientific community convinced planners that the site could support a long-term underground program. This led to the second phase, CJPL2, which expanded the project into a large underground complex. Plans drawn up in the mid-2000s called for 8 sizable experimental halls, each more than 60 meters long and tall enough to house huge shielding tanks and cryogenic systems. These halls were built off a bypass tunnel connected to the original traffic route, turning the once simple layout into something closer to an underground village. The finished version of this expansion is known as DERF, and it transformed the scale of the lab. With around 330,000 cubic meters of total volume, it became the largest deep underground laboratory by space. The layout of CJPL2 is arranged with purpose. The halls sit off the bypass tunnel in an orderly line, each connected by short drifts that keep heavy traffic separated from sensitive work areas. Some halls include deep pits below the main floor so that bulky detectors can grow upward without crowding the space. Surrounding the main halls are smaller service corridors, mechanical rooms, ventilation shafts, electrical substations, and water lines. The design layers support systems around the experimental zones, so that each hall has the quiet conditions needed for precision work. From the beginning, the goal has been to create an environment for low background physics. That means controlling every source of radiation, even the ones we never think about. The designers selected building materials with low levels of radioactivity and tested concrete batches before use. They measured gamma rays, radon levels, and neutron backgrounds throughout the halls and shaped the air handling systems around those findings. The result is a space where the natural noise of the world is stripped away as much as possible, allowing rare events to stand out. Working inside a mountain also comes with practical benefits. Experiments require large amounts of electrical power, cooling water, stable communication lines, and strong safety systems. CJPL draws on the hydropower project's infrastructure to supply all of that. Dedicated high-voltage feeds deliver electricity, and multiple transformers manage the load. The long tunnels allow placement of cooling pipes, fiber optic cables, and ventilation ducts. It functions like a small underground city built with science in mind. CJPL has now become a national research platform with projects on dark matter, neutrinos, nuclear processes, and even geophysics. International teams collaborate there, bringing new detectors and ideas. One of the most focused of those dark matter projects is CDEX itself. How CDEX looks for dark matter. Deep inside the China Jinping underground laboratory, the China Dark Matter experiment turns a piece of ultra-pure germanium into one of the most sensitive listening devices on Earth. The whole idea behind CDEX is simple to describe yet incredibly hard to pull off. If dark matter is made of weakly interacting massive particles, then every now and then one might collide with a germanium nucleus and release a tiny burst of energy. CDEX tries to be quiet enough and sharp enough to catch that burst. The team uses high-purity germanium detectors at very low temperatures and surrounds them with layers of shielding so that almost everything that is not dark matter gets pushed aside. Germanium is a semiconductor, which makes it a great match for this kind of work. Its electrons sit in a stable arrangement until something energetic comes through and shakes them free. When that happens, the crystal forms tiny pairs of charges, and the number of these pairs reveals how much energy was deposited. That feature turns the crystal into a sensitive radiation sensor. Many nuclear physics experiments already rely on germanium because it offers precise energy readings and has enough density to make it efficient, so CDEX could build on a familiar foundation. The challenge is that normal detectors are not sensitive enough for the faint signals CDEX is after. A dark matter interaction might sit thousands of times below the energy of an X-ray, so the entire setup has to reach thresholds so low that even a few hundred electron volts matter. To do this, CDEX uses a special type of detector called a P-type point contact device. Instead of spreading the electrodes across large surfaces, the design focuses one electrode into a tiny point, while the rest of the outer surface carries the opposite charge. That shape reduces the detector's electrical capacitance and cuts down electronic noise. Lower noise means the detector can hear gentler signals without getting confused by random fluctuations. Early versions like CDEX-1 and CDEX-1B used crystals weighing around a kilogram, yet they were already sensitive to energy depositions below 1 kilo electron volt. Later runs pushed that threshold even lower, opening the door to searches for lighter dark matter particles that other detectors struggle to see. Calling these detectors ultra-pure is not exaggeration. Even a tiny amount of radioactive material inside the crystal can spoil the data by creating unwanted signals. For that reason, the germanium is purified to extraordinary levels, removing contaminants until only a handful of unwanted atoms remain in trillions. The crystals are grown and shaped in clean environments, and everything from the way the electrodes are formed to the way the crystal sits in its container is designed to limit any region where stray events might sneak in. CDEX maps out the behavior of the crystal in great detail, studying how charges drift across every region so that later, when an odd signal appears, the team can tell whether it came from a clean part of the crystal or from an edge or surface they need to treat with caution. Temperature is another piece of the puzzle. Germanium detectors are cooled to about 77 Kelvin, which is the temperature of liquid nitrogen. This reduces the number of charge carriers that appear naturally due to heat and improves the clarity of every signal. CDEX-1 used a simple cryostat with a cold finger that carried cooling from a separate liquid nitrogen reservoir. Later setups like CDX-10 placed whole arrays of detectors directly inside a liquid nitrogen tank, turning the cooling system itself into part of the radiation shield. Cold operation also helps keep the response stable across long data runs, which is important because these experiments often collect information for months at a time. When CDEX measures dark matter interactions, it is usually looking for elastic scattering. A WIMP enters the crystal, hits a nucleus, and sends it recoiling. That recoil disturbs the lattice and creates a small packet of charge. Because the point contact design concentrates the electric field near the tiny electrode, the shape of the resulting pulse tells the team where in the detector the event happened. Events deep inside the germanium create pulses with consistent timing, while interactions near the edges or surfaces look different. CDEX uses this information through pulse shape analysis to weed out events that do not match the profile of a clean nuclear recoil. The equipment around the crystal is just as deliberate. In its first form, CDEX-1 wrapped the detector with a sodium iodide scintillator that lit up whenever a gamma ray continued past the germanium. If both detectors fired together, the system marked the event as background and removed it. Around that, the team added copper, lead, and polyethylene to block radiation from the room and from the detector's own materials. CDEX-10 expanded this idea by placing an array of detectors inside a large liquid nitrogen tank, which added a thick uniform shield while cooling everything at the same time. Gathering data from such a setup requires careful work. Low-noise amplifiers sit close to the detectors, and the system records full waveforms so physicists can examine tiny features later and remove events caused by vibrations, electrical interference, or activity at the surfaces. Regular calibration runs keep the energy scale precise, and long background runs help map out what the detector sees when everything is quiet. And once that quiet picture is clear, the real question becomes what's missing. If you like hidden world science, underground labs, remote observatories, extreme instruments, hit subscribe and drop a mountain emoji below. It helps this channel reach more people who love this kind of deep science. What no signal yet really means. When physicists say CDEX has seen no signal yet, they are not saying the detectors sit in total silence. The germanium crystals are always picking up tiny flashes of energy from ordinary sources like natural radioactivity in the rock, trace impurities in materials, faint leftovers from cosmic rays, and the occasional electronic hiccup. What no signal means is that once all those known backgrounds are modeled and compared to the data, nothing remains that looks like a clear hint of dark matter. Every event recorded so far fits comfortably within what you would expect from everyday physics. That might sound anticlimactic, yet in dark matter research, a clean null result can be just as valuable as a discovery. The analysis behind this is heavily statistical. CDEX runs its detectors for long stretches, often collecting hundreds of days of exposure with both its single-kilogram instruments and later 10-kilogram arrays. Once the data are in hand, the team builds a model of what the energy spectrum should look like if only background sources were present. That model includes emissions from tiny amounts of radioactive material in the detector parts, gamma rays and neutrons created in the surroundings, and any lingering particles that still manage to slip through the shielding at Jinping. Researchers fit this model to the measured spectrum, adjusting within physically reasonable limits. If dark matter were scattering off germanium nuclei above a certain rate, the data would show an excess in specific energy ranges, or a shape that rises above the background model. Instead, the observed spectrum stays within the uncertainties of the background alone. Once the team is confident that no obvious signal is hiding in the data, they turn that absence into a scientific boundary. This is where exclusion plots come in. On one axis sits the possible mass of a dark matter particle. On the other sits the strength of its interaction with normal matter. For each point, CDEX can estimate how many events it should have seen if dark matter behaved that way. If the predicted signal should have been unmistakable but nothing appeared, that point is ruled out at a specific confidence level. Any viable dark matter particle must lie below the exclusion curve, interacting even more weakly than the boundary set by the data. CDEX plays a special role in the global effort because it is highly sensitive to low-mass dark matter. Older experiments worked best for particles heavier than about 10 giga-electron volts. By pushing its energy threshold down to a few hundred electron volts, CDEX-1 and its upgraded runs could explore masses just a few times heavier than a proton and even dip below 2 GeV. Those results showed that any spin-independent interaction stronger than a certain level is incompatible with the data. The 10-kilogram CDEX-10 array, with cleaner backgrounds and similar thresholds, tightened those limits further and closed off more of the low-mass landscape. CDEX's work does not stop at simple interaction models. Early searches often assumed dark matter interacted through a heavy mediator that produced a nearly momentum-independent signal. CDEX has since broadened its scope by applying effective field theory and models with light mediators. In those cases, the force carrier has a longer range, and the scattering pattern changes. Analyses of CDEX-10 data under these ideas have set new bounds in the 2 to 5 giga-electron-volt mass window, and even placed pressure on theories involving self-interacting dark matter, or particles that couple weakly to photons. Every time no signal appears, an entire section of theoretical space becomes less plausible. Null results can also be explored by looking for time-dependent patterns. If Earth moves through a relatively smooth halo of dark matter, the interaction rate should change slightly over the year. Some experiments, most famously DAMA, have reported such an annual modulation. Since CDEX uses germanium, similar to past low-threshold experiments, it is an important check. An analysis of CDEX-1 data found no seasonal variation beyond what normal background fluctuations would produce. Those results sit in tension with the idea that DAMA's signal is caused by standard low-mass dark matter. The absence of a signal has another consequence. For years, the preferred picture of dark matter involved WIMPs in the tens of giga-electron-volts range. As experiments like CDEX shave away more of that landscape, attention shifts to a wider set of ideas, including very light dark matter, exotic bosons, hidden sector particles, and other possibilities that interact even more faintly. CDEX does not reveal what dark matter is, but it delivers firm guidance on what it cannot be. A null result from CDEX does not mean dark matter is not real. It simply means that if dark matter interacts with normal matter at all, it does so at levels below the experiment's reach, or through channels that germanium detectors cannot pick up. Still, each carefully studied absence narrows the search. Bit by bit, CDEX helps chart where future experiments should look, and where the universe has clearly said no. And those shrinking possibilities naturally shape what the next generation of underground physics must pursue. The future of underground physics. If the early years of the China Jinping Underground Laboratory were spent proving that a remote, ultra-deep science base could even function, the next chapter is about discovering how far it can stretch the boundaries of underground physics. The second phase of the lab, now known as DERF, has only recently gone live. It was intentionally built on a scale far larger than current experiments require. With more than 300,000 cubic meters of usable space, dedicated power lines, cryogenic systems, and low radioactivity experimental halls, the facility is designed to serve as a home for future detectors that have not yet been built. The goal is not a single flagship instrument, but a full campus of experiments exploring dark matter, neutrinoless double beta decay, nuclear astrophysics, and precision neutrino physics side by side. One of the most ambitious elements of this plan is the Jinping neutrino experiment. Neutrinos barely interact with ordinary matter, which makes them hard to detect, but perfect candidates for studies in a quiet underground lab. A 1-ton prototype at the earlier CJPLI site has already tested background levels and detection methods. The next step is a multi-100-ton liquid scintillator detector that will occupy one of the new halls, planned for installation around 2026. This detector aims to observe low-energy neutrinos from the Sun, radioactive decays inside Earth, and distant supernovae. Jinping's depth gives it an advantage because those faint signals are easily drowned out at the surface. The experiment hopes to refine measurements of solar fusion processes and to improve estimates of Earth's internal heat through direct detection of geoneutrinos. Alongside this sits a project with a completely different focus: underground nuclear astrophysics. The JUNA experiment uses beams of particles fired at thin targets to measure fusion reactions at energies similar to those found in stars. At the surface, background radiation overwhelms the tiny signals from these reactions, but underground the noise drops to a level where the physics becomes visible. JUNA has already produced important measurements of proton capture reactions that influence how elements are formed inside stars. Plans for a JUNA 2 platform include stronger accelerators, better beamlines, and more flexible target systems, turning part of Jinping into a controlled miniature star environment for refining stellar models. Future dark matter searches at CJPL will also expand. The lab already hosts xenon time projection chambers from the PandaX program and germanium arrays from CDEX, both of which have long-term plans for larger detectors with lower backgrounds. DERF is equipped with the infrastructure needed for these upgrades, including large water shields, liquid nitrogen tanks for cooling and shielding, on-site copper electroforming facilities, and radioassay labs capable of screening materials to extremely low contamination levels. As the global community pushes toward ton-scale and multi-ton detectors, Jinping's combination of depth and road access becomes a practical advantage. It is one of the few places where massive cryogenic systems can be installed and maintained without the limits of a vertical mine shaft. Looking ahead, one major challenge is the so-called neutrino floor. As detectors become more sensitive, neutrinos from the sun and the atmosphere begin to mimic dark matter events. At some point, neutrinos become an unavoidable fog. Underground labs around the world are approaching this regime, and future strategies may involve comparing results from multiple sites, using different detector materials, or searching for subtle directional information. Jinping's distinct location and rock composition give it a unique background profile, which helps when cross-checking hints seen elsewhere. CJPL is part of a wider international network. In Italy, huge xenon and argon detectors are searching for dark matter beneath the Gran Sasso Massif. In Canada's Snow Lab, cryogenic germanium and silicon detectors are being tuned for low-mass dark matter and exotic particles. In Japan, large water and scintillator detectors study neutrinos from accelerators and supernovae. New labs are being built in South America and other regions as well. Underground science is also becoming more interdisciplinary. The quiet, stable conditions that help particle physics are valuable for geology, seismology, and even biological research. Chinese science agencies describe DERF as a platform that will bring together work on particle physics, nuclear processes, and life sciences. As the facility matures, researchers may use it to study how microbes evolve in low radiation environments, or how deep rock layers respond to stress over long periods. The future of underground physics is no longer a single search, but a broad effort to explore a hidden side of the universe. Whether dark matter appears soon or remains elusive, labs like Jinping will keep shaping our understanding by offering places quiet enough to let the universe speak. As these underground experiments grow sharper and more ambitious, we may be closer than ever to hearing what the universe has been hiding. Which breakthrough do you think will arrive first? Let us know in comments. If you want to keep exploring these mysteries with us, like the video, subscribe, and share it around.